Swayam Prabha. Digital India. Educated India.
So welcome students. Now we are going to do some practice problems on non-ideal reactors. Let's see the first problem. Here, if you can see, the C pulse curve is given. The problem states that the dispersed non-coalescing droplets with the reactant concentration given as 2 moles per liter reacts to give the product as it passes through a contractor. Now this contractor, the reaction kinetics, this follows a second order reaction kinetics where the reaction rate constant value is given to us. Now the average concentration of A, which is remaining in the droplets, we need to determine if the RTD is shown here. So we know now they have used a C pulse tracer experiment. But if you notice, the unit of this is minute inverse. This indicates that this C pulse is equal to the E curve. So the area in the shaded region is equal to 1. So therefore your E value at this point from between 1 to 3 is nothing but we can calculate. So this will come out to be 0.5. So we need to find out what will be the residual concentration of A after the reaction, after it comes out of the contactor. So the reaction rate constant is given, it's a second order reaction rate. So the initial concentration is known, it is a second order reaction. So dCA by dt is what is kCA square. It's a reactant, so the negative sign. Now we can integrate this to see how Ca is related to, will change with time. So if we integrate this, putting the limits of Ca naught, Ca between 0 to t, then we will get Ca by Ca naught. Now if we substitute the values Ca naught and K given here, it will become 1 by 1 plus T, which is nothing but the fraction of Ca by Ca naught. Now E curve we know is C pulse divided by the area under the curve, and by convolution integrals, if you remember, this fraction will be so this is actual and this is theoretical. Now we know that Ca by Ca naught between 1 to 3, this can be given by the function 1 by 1 plus t. The E value in this time is 0.5 and we can, the integral limits will be between 1 and 3. So if we solve this, we will find that your actual Ca by Ca naught fraction comes out to be 0.347 and not just as it would have been with 1 by 1 plus t. So the actual conversion can be given as 1 minus Ca by Ca naught conversion fraction, so which will be equal to 0.653, and in percentage it becomes nearly 65% conversion due to the non-ideality. Let's see the problem 2. A large tank, 860 liters. This is used as a gas liquid contactor. Gas bubbles, they rise up through the vessel and they move out from the top. The liquid flows in at one part and it leaves from the other at a flow rate of 5 liters per second. Now, in order to get an ideal flow pattern of the liquid in the tank, a pulse of the tracer, the amount of the tracer is given as 150 grams, has been injected at the liquid inlet and the concentration of the tracer is being measured. When it was measured, the concentration looks like this, as shown in the figure 2. Now, what is being asked to check is if this is a properly done experiment. Now, in order to check that this is a properly done experiment, we can do a material balance over the tracer. We know the total amount of tracer is 150 grams. So, the concentration curve is given to us. So, sum of area of all the C curve which is given here will be equal to capital M by small v. Small v was the volumetric flow rate, which is 150 by 5 liters per second. So, this value comes out to be 30 grams second per liter. So, if we want to find, then let us do the sum, which is A1 plus A1 by 4 plus A1 by 16, A1 by 64 and so on. So, if we take A1 common, the series will become like this. So, this is nothing but seems to be a geometrical series with an R value of 1 by 4. So, an infinite geometrical series, if you sum up with an R value of 1 by 4, you will get the value of 4 by 3 and you substitute the value of A1 here, which can be obtained from the plot, and thus we get the total area as 0.5. This is grams minute per liter. Please note, as the time is given here is in minutes. So, we will have to convert this 30 grams liter seconds into minutes. So, this will be dividing by 60. So, it comes out to be 0.5. So, now we see that the theoretical area is equal to the area under the C curve obtained. So, this shows that the experiments has been conducted properly. Now, we also need to find out the liquid fraction in the vessel. For that, we need to first find how much is the volume of the liquid in the vessel. Now, in order to find the volume of the liquid in the vessel, we will have to, we know the volumetric flow rate. So, mean residence time is V by F. So, your volume can be given if the volumetric flow rate can be multiplied by the mean residence time. So, mean residence time, knowing the C curve, can be calculated using discrete time intervals. So, if you do this, which is summation of T C delta T by summation C delta Ti. So, if we do this, what is Ti? 2, then 4, 6 and so on after every 2 minutes. So, this is what, and then it is the area C delta I. So, which is being multiplied here, A1, then A1 by 4, A1 by 16 and so on, and this is the divided by the total area under the curve, which we have already calculated as 0.5. So, if we do this, this is again, if you take 2A1 common, this will end up in Taylor series, an infinite series, and we can sum up and it will give you the value of 2.67. So you need to have a little bit of revision of your geometrical series, arithmetic series, summations, or Taylor series expansions for infinite series. So then you will be able to reach here. So for that you take a 2a1 common here, so it will get converted to a Taylor series. So once we know this mean residence time, we can calculate the volume knowing the volumetric flow rate. So volumetric flow rate was given as 5 liters per second, has been converted to minutes because this is in minutes. So therefore we get the total volume of the liquid, which is 800 liters. So now we need to calculate the volume fraction. The total reactor is of the volume 860 liters. So volume fraction in the vessel would be 93%. So the remaining would be gas fraction, which comes out to be 7%. Now third part of the problem is to find the E curve. So we know that C pulse curve can be converted to E curve by dividing the C values by the total area under the C pulse curve. So area under the curve we know is 0.5. So the entire curve can be made two folds. The values, the corresponding C values can be converted two folds to give the corresponding E values. So this is what has been done here. So the area for the first plot will become 3 by 4 twice and so on for the rest of the spikes. Now the fourth part says qualitatively what do you think is happening in the vessel. So if you remember, spikes coming out at small intervals, regular intervals with decreasing area, or the peak is decreasing, demonstrates that there is some internal recirculation happening.